Welcome! Have you ever looked at these massive AI models and just wondered, how on earth do they build those things? Well, it turns out it's a two-part story, and in this explainer, we are going to unpack that exact playbook. We'll look at how they first handle the brute force scale of it all, and then how they refine all that raw power into some seriously sharp, precise intelligence.
All right, let's just dive right in. The number one challenge facing literally every major AI project today is the problem of sheer scale. I mean, the models themselves and the mountains of data they need to learn from are just way too big for any single computer to handle. So what do? How do you solve that?
Here's the game plan. First, we're going to tackle the brute force problem. How do you actually train these things across tons of machines all at once? Then, we'll switch gears and get into the brains of the operation, the whole fine-tuning workflow that takes all that power and turns it into real precision.
So, you might be thinking, why not just build a bigger, beefier computer? Well, it's not that simple. Let's get right to the core of why the old ways of doing things have completely hit a wall.
Here's the bottom line. Our ambition for what AI can do has just completely outpaced what a single piece of hardware can handle. Think about it like trying to download a movie that's bigger than your computer's entire hard drive. It's just not going to work. And that's exactly the situation we're in with models that have hundreds of billions of parameters and datasets measured in terabytes.
Okay, so if one machine isn't enough, the obvious next step is to use a whole bunch of them, right? And that brings us to our first major strategy, training in parallel. This is where we get a whole fleet of computers to act like one big super brain. And there are basically two main ways to pull this off. First, you've got data parallelism. This is like giving a whole team the same textbook, but each person only has to study a different chapter. They all learn at the same time, just on different parts of the material. Then you have model parallelism. This is for when the textbook itself is so massive that no single person can even lift it. So here, the team has to work together just to read one gigantic page. Which one you choose really just depends on your biggest problem. Is it the size of your data or the size of the model itself?
And this is how that divide and conquer approach actually works. First, you take a big chunk of data and split it up. Each machine crunches its little slice and comes up with a gradient, which is really just its own little suggestion for how the model can get better. Then comes the magic part, step 3. All reduce. This is where all those individual ideas get collected and averaged out into one single powerful update. And finally, that one big update gets sent back to every copy of the model so they all learn the exact same lesson and stay perfectly in sync.
Okay, so getting this to work is one thing, but getting it to work fast, that's a whole other challenge. And that's where these pro tips are absolutely golden. A massive slowdown is just the network chatter between all the machines. So the trick? You compress the updates before you send them. It's a simple idea that can slash your network traffic by half or even 75%. And another lifesaver is checkpointing. Basically, saving your work often. These training jobs can run for weeks. You absolutely cannot afford to let one little crash send you all the way back to the beginning.
But look, having a super powerful model isn't the whole story. It also has to be accurate, relevant, and, trustworthy. And that brings us to the second act of our playbook, the art of refining all that raw power into surgical precision.
Our first tool for this is something called Retrieval Augmented Generation, or RAG for short. Think of it like this. A normal AI only knows what it was trained on, and that information could be months or even years out of date. RAG fixes this. It gives the AI a library card to the entire internet. Before it answers your question, it can go look up the latest, most relevant information, making sure its answers are actually grounded in today's facts, not yesteryear's.
And the second tool is fine-tuning. So if RAG is all about giving the model better information, fine-tuning is about making the model better at using that information. You take a general, jack-of-all-trades model, and you keep training it, but this time on a much smaller, specialized data set. You're basically sending it to grad school to become an expert in one specific topic or style.
Now here is the most important part. These two things, RAG and fine-tuning, they're not an either-or choice. No way. The real magic, the state-of-the-art stuff, happens when you put them together. That's how you build a system that's both incredibly knowledgeable and incredibly intelligent.
So let's walk through how this pipeline works. A user asks a question. First, the system turns that question into numbers so it can understand the meaning. Then, the RAG system kicks in and fetches the most relevant documents from its knowledge base. And finally, everything, the original question and all those juicy facts it just found, gets handed over to the fine-tuned model. And because it's an expert, it can synthesize all of that into a single, coherent, and really accurate answer.
And this isn't just theory. The results are absolutely stunning. This chart shows accuracy. A basic model using RAG gets a pretty good score, 78%. But look what happens when you swap in a model that's been fine-tuned for this specific job. The score skyrockets to 92%. That's a massive jump, and it's because that fine-tuned model knows exactly what to look for. It can find the signal and all the noise from those retrieved documents.
This makes a huge difference in the real world. For example, in one telecom company, using this hybrid approach cut down on customer support tickets getting escalated by 28%. A huge number. And why? Because the AI wasn't just guessing anymore. It was giving accurate, context-aware answers, citing the correct tower IDs instead of just making them up. So, if you're thinking about implementing this yourself, here's a key piece of advice from the experts. Start by fine-tuning the generator. That's the part of the AI that actually writes the final answer. It gives you the biggest bang for your buck because you're not just giving the model better facts to work with, you're fundamentally teaching it how to be a better thinker and a better writer with those facts.
All right, let's bring it all home and summarize this modern AI playbook. It's really a tale of two halves. First, you conquer the scale, and then you master the precision.
This table just lays it out perfectly. On one side, you've got the scale problem. The models and data are too big. The solution? Distributed training. On the other side, you've got the precision problem. The models are too generic or inaccurate, and the solution there is that powerful 1-2 punch of RAG plus fine-tuning. It's power and it's precision.
And that kind of leaves us with one final big question. We figured out the playbook for today, how to get more power through scale and more precision through refinement. But what about tomorrow? Where will the next truly giant leap in AI come from? Will it be from just building even bigger, more powerful models? Or will it come from finding even smarter, more elegant ways to fine-tune them?